Hello, good evening, friends. Myself, Ankush Gupta, here at the Gate Coach. And today we are here to discuss the solutions for some of the questions from this mock test. Okay, so I am hoping that all of you have attempted this paper in chemical engineering. We will discuss the chemical engineering solutions here. Okay, and obviously not for all the solutions. As you can see in your test portal, solution and explanations for all the questions is already there, but still I felt like we should discuss some of the questions which are very basic and some important questions, conceptually strong. So that's why we are here and we will discuss those questions. Okay, so I hope you enjoyed this paper, and as you have attempted the test paper, so you already have this test paper with you. Otherwise, you can go in the result section of your portal, test portal, and there you can see the test paper. Okay, so I will discuss the questions which I will discuss here today are from mock test of December 18, 2022. I will discuss some of the questions like question number 2, 8, 9, 16, 17, 18, 22, 24, 30, apart from that 32, 40, 42, and 43, 47. So these are the questions which we will discuss here in this video. As you have attempted the paper, so one thing you must have seen that this paper was totally based on the GATE syllabus and the latest GATE pattern as well, where you have the questions in shuffled form. 1 mark and 2 mark questions are shuffled there in reshuffled form. Okay, so we tried that this entire paper is based on that only. So let's start from the topic only, and later on in the video, after the discussion, I will also discuss some very key points which I feel will be important and helpful for all of you to shape your preparations, to finalize your preparations for the GATE 23 exam. Okay, so if you see the question number 2, it is given that a system receives 0.7 kg per second of a fluid at a velocity of 40 meter per second at an elevation of 25 meter. At the exit, the elevation, this is at the inlet, and now the exit conditions. The elevation is Z2, that is 50 meter. The fluid leaves at a velocity of 10 meter per second. The specific enthalpies of entering and leaving fluids are, so H1 here is 2700 kilojoule per kg, and here H2 is specific enthalpy 2900 kilojoule per kg respectively. If work done by the system is, as you can understand, this is the open system because mass flow takes place, so obviously this will be the shaft work, which is 5 kilowatt, or you can write it as 5 kilojoule per second. Determine the heat transfer up in kilowatt up to 2 decimal places. So this is one open system problem, and I hope you know that whenever we have a open system problems of heat and work in thermodynamics, obviously we can use the steady flow energy equation. And if you guys know, from a steady flow energy equation, it will be the heat supplied Q12 plus the energy entering by the with the fluid, and here we will have specific enthalpy, specific kinetic energy, and specific potential energy equal to the work done by the system plus the energy leaving along with the fluid. So here also we will have the specific enthalpy, specific kinetic energy, and specific potential energy. So this is the equation which you can use, and here as you can see they have not mentioned anything regarding the fluid or its flow rate except the inlet flow rate. So we can consider that M1 is the mass flow rate at an inlet and at outlet is same. That's why there is no accumulation of mass. So M dash and M double dash term will not be there. Okay. And if you want to understand the steady flow energy equation, how we got this equation or how we can apply this equation and how to drive this equation for any open system, then you can mention that in the comment. We will share the link of the video where we have discussed the application of first law of thermodynamics on open system. Okay, so just mention that thing in the comment box, or for any other topic we will share the link of those videos. Okay, otherwise you can watch them, you can search them on our YouTube channel. So but here H1 V1 G1 is given, H2 V2 Z2 is given, shaft work is given, mass flow rates are known, so you can find out the heat transfer and you will get your answer. So I don't think we can be required to do the calculations here. You can get that from the paper itself if you have any doubt. Next is question number 8, and question number 8, if you see, that is also based on the thermodynamics and open system, and the same you can do with the help of steady flow energy equation on the nozzle. Okay, so if I hope you know that nozzles are the devices which are used to increase the velocity of the fluid by decreasing the cross sectional area. Similarly, we have the diffusers devices where we increase the cross sectional area to decrease the velocity. This is the nozzle and this is the diffuser, opposite to it. Okay, so eighth also you can do by the same way. Then I will discuss question number 9 with you. In question number 9, if you see, that is the very basic question from the process calculation part. We have 3 kg oxygen, 5 kg nitrogen, and 12 kg CH4. And they are asking about the mass fraction and mole fraction of oxygen. So what you need to do here, when all the things are required, so just draw a table simply. Here on the first column, write down the components in row wise: oxygen, nitrogen, and CH4. Then their amount which is given. So like here mass is given. So first we will write the mass as 3 kg, 5 kg, and 12 kg. So here you guys can calculate the total mass. That will be 20, as you can see. So the mass fraction, you can see mass fraction, as you know, the mass of component I divided by total mass. So that will be 3 upon 20, which is 0.15. Okay. Now if you need to calculate the mole fraction as well, so just write down their molecular weights in another column. For oxygen it is 32, for nitrogen 28, and for methane it is 16. And then in the next column find out the number of moles. And I hope you know that number of moles is mass of the component divided by molecular weight. If mass will be in gram, so that is gram mole. If mass will be in kg, that will be kilomole. And if mass is in pound, that will be kilomole, pound mole. So here oxygen Mass divided by molecular weight, 3 divided by 32. That will give you the number of moles of oxygen, which will be 0.09375. Mass of nitrogen will be mass divided by molecular weight, that is 0.1786 approx. And for CH4, mass divided by molecular weight is 0.7500. And now here calculate the total moles and you will get your answer after that. It will be 1.02235. So now you can calculate the mole fraction. That will be moles of component divided by total moles. So moles of component 0.09375 divided by total moles 1.02235. So you will get 0.0917. That is your answer. This is the one way by which you can do your calculations. Otherwise, there is another way by which you can directly calculate answer. Okay. So like here, if you see, mass fraction will be mass of component divided by total mass. That is this. So it is 0.15. Okay. But if you want to convert this mass fraction directly into the mole fraction, then you can calculate by simply, see, this is the mass fraction, just write it here, divided by total mass fraction. Total mass fraction is, and you can break it as mass fraction of components like this. For nitrogen, it will be 5 divided by 28. Sorry, 5 divided by 20, that is 0.25. And for CH4, it will be 12 divided by 20, that is 0.60. So just write the mass fractions like this, mass fraction of component divided by total mass fraction in the form of summation. Okay, and now you know that if you have to convert mass into moles, then what you have to do? You have to divide it by molecular weight. Similarly, now here divide them by their respective molecular weights. This is for nitrogen and this is for methane. And after solving this, also you will get the same value. So that's how you can do it directly. Okay, although we have discussed the same methods again and again many times in our classes, but for the people who are outside the TGC, so that's how you can do this. Okay, so next question, 9 is done. Next is question number 16. So if you see question number 16, for a liquid phase reaction operating in a PFR, the conversion obtained is 50%. If the existing PFR is replaced by equal size MFR, then the conversion obtained will be. So this thing we have discussed many times in our class, the comparative study between ideal MFR and PFR, and I hope you guys remember those points. Like for positive order reaction, if you compare the MFR and PFR, if you take the MFR and PFR of same volume, the conversion obtained by PFR will be more than that of obtained by MFR. Okay, and similarly for positive order reactions, if you talk about the volume for same conversion, then volume required by MFR will be greater than that of required by PFR. Simple. Okay, so like in this question, PFR gives 50% conversion. So what will be the conversion of MFR? That's what they are asking. Okay, and for zeroth order reaction, if the volume of reactors are same, MFR and PFR, then the conversion obtained by them will also be same. Okay, I hope you already know that. Otherwise, you can check that from the design equation. Just put minus RA equal to K for zeroth order reaction, and you will see the final design equation in both the reactors MFR and PFR will be same. So that means for same conversion, volume will be same, and or for the same volume, conversion will be same. And similarly, the next is for negative order reactions. If you take the MFR and PFR of same volume, then the conversion obtained in MFR will be greater than that of obtained in PFR. Or if you take the same conversion for MFR and PFR, then the volume required by MFR will be smaller than that of required by PFR. Okay, I hope you understand this. So here one thing which I hope all of you already know, that if we are comparing the MFR and PFR for same conversion, for the constant conversion, then the ratio of their volume increases with order of reaction. Like if you increases the order of reaction, then this ratio will also increase, the ratio of their volume. Okay, so in question number 16, you can see first option, MFR will have more than 50% conversion if order is less than 0. So that's the correct answer. Correct. MFR will give higher conversion for negative order reaction as compared to PFR of same volume. And second option, if order of reaction is positive, then conversion will be less than 50%. That is also correct. Now the third option, C, equal to 50% for an order of reaction. No, we don't know. I think it should be any order. Okay, it is typing error. And D is equal to 50% for n equal to 0. That is also correct. I hope you understand this. Okay, so here the correct options will be A, B, and D. This was your MSQ type question. So in GATE exam, in MSQ type question, when you will choose all the correct options, only then you will get full marks, otherwise you will get 0 marks. Okay, so this is question 16, and similarly there is a question 17, which I hope all of you understand. That is also very basic question, easy but little bit tricky because of the statements. Okay, so if you are careful with the words and their meaning, if you know all these things, then you can easily solve question number 7. That's not a difficult question. Okay, but if you are unaware with the meaning of the terms, if you are not careful with the words, then it will be difficult for you, it will be tricky for you. Like in question 17, it is given that consider the following statements about the properties of perfect non-reacting gas mixtures and find out which of the above statement is or are correct. So option A, total volume of a mixture is the sum of partial molar volume at the same pressure and temperature. That's the correct option, because you know that the molar property of the solution is the summation of xi into mi bar. Okay, and this is perfect gas mixture, so obviously ideal mixture. So in ideal gas mixtures also, I hope you understand that for ideal mixtures, for ideal solutions, the partial molar volume and molar volume will be same, and partial molar enthalpies and molar enthalpies of the components will be same only, but not their entropy or Gibbs energies. Okay, so second option, entropy of the mixture is the sum of entropies of the constituent. No, because for ideal solutions, partial molar entropy and molar entropies are different. So that's why S will be equal to summation of SI bar, not SI. So B is incorrect option. Okay. C, total pressure of the mixture is sum of partial pressures of the substance. That is correct as per the Dalton's law, you know that. D, mole fraction of the mixture is equal to pressure fraction and volume fraction. That is also correct as per the ideal gas mixture, you know that already. So here the options will be A, C and D. So I hope it is clear to all of you. And if you want the solution for any specific question from this paper, you can comment that also in chat box, in the comment box. So 16 done, 17 done. Now question number 18. I hope you can do it as well. Question number 18 is from mass transfer. Mass transfer coefficient of naphthalene in air is given 5.8 into 10 to the power minus 3 meter per second. So you can see this is the gas mixture. Air means gas mixture, and units of mass transfer coefficient is meter per second. So obviously this is what? This is Kc, which is given, means mass transfer coefficient in terms of concentration. Naphthalene is evaporated in a stagnant air film at 400 Kelvin, means that is what the case of diffusion of A through non-diffusing B, DND case, and the total pressure is 1 atm. Vapor pressure of naphthalene at 400 Kelvin is determined by the Antoine equation and given as 0.01 atm. Under these conditions, if the diffusivity of naphthalene is given for question number 18 here, diffusivity is given as 0.95 into 10 to the power minus 5 meter square per second. Then calculate the thickness of air film around the naphthalene ball. Okay, so you know that if naphthalene is diffusing in air, so this is the case of DND, and you can use the two film theory for that. Okay, and as per the film theory, I hope you guys know that mass transfer coefficient will be equal to diffusivity over delta. And here you can calculate delta by putting the values of Kc and DAB. Simple. Okay. So you just need to use the film theory here. Okay. If this the similar question they ask to, means the similar question they can ask you if the component is suspended in a bulk phase. Okay, like air bubble is rising in liquid, for example. So the where the components are dispersed in other phases, like gas is dispersed in liquid, so there you can use the penetration theory to calculate the mass transfer coefficient. Okay, so 18 is also done. Hope it is clear to all of you. Okay, next is question number 22, and 22 is from CRE, and I hope you can do it as well. You must have done it. It is one of the very easy question. So here the reaction 4PS3 gives P4 plus 6S2. This is the reaction, and since it is gas phase reaction, so you can see overall stoichiometric coefficient is 7 plus 1 minus 4, that is 3, which is non-zero. So obviously it is a case of VVRS. Obviously it is a case of VVRS. Anyways, here rate equation is given minus RPH3 equal to 85 R inverse concentration of PH3, where you have to calculate the volume of PFR for 80% conversion, and operating temperature and pressures are given 500 degrees Celsius, T is 500 degrees Celsius, or you can write it as 773 Kelvin, and pressure is 5.5 atm. Okay, so here you have to find out the volume of PFR if 2.5 kilomole PS3 per hour is introduced. So if we consider PS3 as A, so XA is given and FA0 is given 2.5 kilomole per hour. So I hope you guys know that for variable volume reaction system, the design equation of PFR is Vp by FA0 is equal to integration from 0 to XA dXA over minus RA. And here if you put the value of minus RA, that will be Kca, And for variable volume reaction system at constant temperature and pressure, I hope you know that Ca is equal to Ca naught 1 minus Xa over 1 plus epsilon A Xa. So here you can solve this integration where K is given 85 inverse. K naught you must have calculated or in question 21. As for gas mixtures, you know that Ca naught we can calculate by using ideal gas law. So Ca naught will be Pa naught over RT. Pa naught means Ya naught into total pressure. Okay. So here Ya naught is 0. Nothing is given. So we will consider the pure feed as they haven't mentioned anything regarding the feed. Total pressure is 5.5 atm. R in terms of atm and mole per liter is 0.0821 atm liter per mole per Kelvin. So I hope you guys know how to calculate R in any respective units with the help of STP condition. And temperature is given as 773 Kelvin. So from this you can calculate Ca naught and epsilon A. I hope all of you know that epsilon A is delta into Ya naught, where delta is nu by A. So here you can see overall stoichiometric coefficient 3, stoichiometric coefficient of A in the reaction 4, Ya naught is 1. So epsilon A will be 0.75. So you can put these values in the equation and you can integrate this to solve. You will get your answer. Okay. So I am not doing any calculation because they are already given in your solutions. You can check that. Okay. Next question number 24. So in 24, you can see it is given that a rate estimate the rate of burning of a pulverized carbon particle in a furnace if diameter of the particle is 4 mm, pressure 1 bar, oxygen available at 1100 Kelvin. Assume that fairly large layer of CO2 is there surrounding the carbon particle. Okay, diffusivity is given. So from Fick's first law of diffusion, I hope you know that. Sorry, from flux equation first. I hope you know that Na will be equal to Ka plus Ia times of Na plus Nb. So here you can understand that carbon particle is burning, so that is going in the air, but air is not going in the solid phase. So Nb will be 0. That is the case of diffusion of A through non-diffusing B. So from this you will get Na equal to Ja over 1 minus Ya. Okay. And from Fick's first law of diffusion, I hope you know that Ja will be equal to minus of dAb into dPa over dr. That's how you can write minus dAb over RT into dPa by dr. That's how you can write Fick's first law of diffusion for the spherical particle. Okay, and you can put this value here and you can integrate that in the suitable limits. Like this is the particle, suppose it is burning and going into the atmosphere surrounded by large bulk air of CO2. So here just at the surface of the particle, this is section 1 you can say, where the partial pressure will be same as its vapor pressure, and here in the bulk, that is section 2, you can see that partial pressure of particle will be 0 because no particle will be present there as such in a significant amount. So we can consider the partial pressure to be 0. And now you can put these values in the equation and you can solve it. You will get your answer. Okay, so that's not a big deal. You can do it easily by yourself. You can see the solution, the steps, calculations, all that stuff. So after 24, we have question number 30, that is from the mass balance. I hope you can see, understand that that's not a big deal. I will not discuss 30 here. I will discuss 32. If you see question number 32, the TS diagram is given for two thermodynamic cycles. For first cycle, it is given as this, and for the second cycle, it is given as this. And you have to find out the ratio of their efficiencies. Okay, so I hope all of you understand that, like PV diagram, you know that for closed system, work done is PdV. So integral of PdV means total work done. So the PV diagram, area under the curve, represents the work done, and for closed system, and similarly for reversible processes, I hope you know that ds is equal to del q by t. So here you can see del q will be equal to TdS. So if you integrate this, you will get total heat transfer. That means the area of TS diagram, area under the curve in TS diagram, will give you heat transfer. Okay, so in a reversible engines, I hope you understand that T1 is the higher temperature, so that is the source. T2 is the lower temperature, so that is for the sink. So area under the first curve, this total area, like you can see this yellow area, that will be equal to QH, the heat taken by the source, taken by the engine from source at temperature Ts. This is the reversible engine, which will produce the work W, let's say W net, and it will reject the heat QL to the sink at TL, let's say. So here, this is yellow area will represent QH in both these cases. Here it will be QH. And similarly, if you see for the source, the area under the curve below the source temperature will give you the area of the sink, the heat transfer to the sink, that you can say QL. And first law of thermodynamics, I hope here you guys know that W net will be equal to QH minus QL. So that means here if you subtract these areas, you will get only the area of this portion, this triangle actually, which will be nothing but equal to work done, W net. And similarly here, area of this triangle will be equal to work done, W net, for the second law. Okay, so you have to calculate eta 1 divided by eta 2. So you can see eta 1 will be W upon QH for the first process, eta 2 will be W upon QH for the second process. So for the first process, W is the area of triangle only. So that will be half base S1 minus S2 into height, that is T1 minus T2, divided by QH, that is this total area, which will be S1 minus S2 into T2, plus area of this triangle, that is half S1 minus S2 multiplied by T1 minus T2. This is for the first process. Similarly, eta 2 will be W, that is area of this triangle only, half base S1 minus S2 into T1 minus T2, divided by QH, that is this total area, which will be, you can see, is a rectangle itself. So that is nothing but T1 into S1 minus S2. So you guys can put this value there and solve, you will get your answer. Okay. The calculation is given in the solution. Okay. So if you know that TS diagram, the area of TS diagram represents heat transfer, then you can easily solve this. Okay. After that, we have question number 47, where it is given that two air streams of mass flow rate 36 kg per minute and 14 kg per minute are introduced and mixed in a chamber where the enthalpies of each stream is 36 kilojoule per dA per kg per dA and H2 is equal to 50 kilojoule per kg dA. dA means dry air, you can say, kilojoule per kg of dry air. Okay, and they are mixed. So what will be the enthalpy of mixture? Nearly. And if you see, all the units are in kilojoule per kg dA. So that means simple enthalpy change of mixing. You can enthalpy of this mixture, you can directly calculate that. See, enthalpy चीज नहीं, enthalpy पूछा है ना आपसे mixture का, तो you know that enthalpy of the mixture when you are adding two stream, so obviously enthalpy is what? Total energy. When two streams are added, so their total energies will increase, so that you can calculate directly from summation xi into hi. Okay, and here you can put the values. X1, that will be x1 h1 plus x2 h2. So x1 will be 36 divided by 50, x2 will be 14 divided by 50. When you add from this, you will get x1 x2, put that value here and you will get your answer. That will be close to 40, I guess. Okay, so that's how you can solve question number 47. And last question which we will discuss here, that is question number 42 from the evaporator. See, this is one evaporator. It is given that a feed introduced in the evaporator at a rate of 10 to the power 4 kg per hour at temperature 30 degrees Celsius. Okay, having 10% salt, and it is concentrated up to, means concentrated solution is leaving, let's say, c kg per hour at with the 20% salt. Feed enters at 30 degrees Celsius, and here we are introducing the steam at temperature Ts, that is 110 degrees Celsius. Okay, the latent heat of vaporization is given 570 kilocalorie per kg. So boiling point temperature of the solution means T set, the saturation temperature is given as 45 degrees Celsius. Okay, and now specific heat of all the components in the solution are 1 kilocalorie per kg per Kelvin given. So you have to find out the heat transfer area if overall heat transfer coefficient is given as 1800 kilocalorie per hour per meter per degree Celsius. Meter square, sorry. Okay. So here overall heat transfer coefficient is given. So I hope you understand that for any heat transfer equipment, the rate of heat transfer we can write in terms of overall heat transfer coefficient as Q equal to UA delta T. Now the question is, what is delta T here? For heat exchangers, it is delta T ln. You know how to calculate that, LMTD. And for evaporators, remember this delta T is the temperature of the steam, Ts, minus the saturation temperature of the feed. In evaporators, we take the driving force as temperature of steam minus saturation temperature of the feed, that is the boiling point temperature. Okay, so here you just need, U is given, A, you have to calculate delta T, you can easily calculate, as you know that steam temperature and boiling point temperature. The only thing is Q. How can you calculate Q? So that is very easy. See, in this question, if you do the overall mass balance, so you know that some vapor is also leaving here, vapor, let's say at V kg per hour. So overall mass balance, total mass in F, that is 10 to the power 4 kg per hour, will be equal to total mass out V plus C. And then if you do the salt balance, you will get total salt in 10 to the power 4 into zero point 0.1 equal to total salt out C into 0.2. So from here you will get C, that is 5000 kg per hour, and thus you will get V as well, amount of vapor produced as 5000 kg per hour. Now, if I am talking about the heat requirement in evaporator, so just understand like this. It is very easy. Energy balance is the easiest thing you can do. And why? Because you can easily visualize everything. Okay. So see, feed is going F in the system. So it will carry some energy. Okay. But we will not talk about all that stuff. We will see how the energy requirement is there and what is that and how it is required. So F amount of feed is going in the system solution at temperature T1. So what will happen? Obviously, this feed will not evaporate directly. If you know the evaporator concept, we introduce the dilute solution feed where some of the solvent is vaporized and we get the concentrated solution. So feed is going in the system at temperature T1. So first we will increase the temperature of the feed from T1 to T set, the saturation temperature. And for that some energy will be required. So let's say that is FCP of feed into T set minus T1. Now the entire feed is at saturation temperature. Now, when the feed is at saturation temperature, then some part of the feed will vaporize. That is V amount. Okay. So for that V amount, if it is getting vaporized, so what is required? Latent heat. So amount of heat required for this vapor to get vaporized is V into lambda. Simple. So that's it. And concentrated solution will leave at saturation temperature only. So that's how you can solve it. So now just put this value here. F is 10 to the power 4 kg per hour. Cp is 1 kilocalorie per kg per Kelvin. T1 T set minus T1 is given as 15 Kelvin. If you know 1 degree Celsius equal to 1 Kelvin for delta T plus V, that is 5000 kg per hour into lambda vaporization is given, that is 570 kilocalorie per joule, sorry, per kg. After this you will get Q, that will be 3 into 10 to the power 6 kilocalorie per hour, I guess. If I am not wrong, you can check. Okay, it is 3 into 10 to the power 6 or what. Yes, 3 into 10 to the power 6 calorie per hour. And value of Q here, where in this equation, where you know that delta T will be Ts, temperature of steam, that is 110 degrees Celsius minus saturation temperature, 45 degrees Celsius, that is 65, I guess. Yes, 65 degrees Celsius. So put this value here and you will get your A. Simple. Okay. So that's how you can solve the problems of energy balance. So guys, as I have told you, this is the solution of some of the questions which I felt are little important and conceptual for you for your preparation. If you find difficulty in any other question, you can comment that in the chat box in the or in the comment box. We will provide you the solution. Okay. Now, one thing which I want to tell you to all of you who are preparing for Gate 23 exam in chemical engineering, see, be smart. Okay. In the remaining time, as you can see, we now less than 60 days are remaining. Okay. It's 18th December today. 12 days are remaining in this month. Forget the Christmas day or the 31st night, because maybe you will be busy in New Year party. Anyways, 12 days are remaining in this, 31 days are remaining in next month, 43, and 10 days are there, 50. So almost 50 days are there. So in these 50 days, you have to do your preparation smartly. And what things you have to keep in your mind while doing all this preparation, that focus or revise mainly those subjects, means give most of your time on those subjects which will help you to score in exam. Okay, don't try anything new. For example, if you are completely unaware with heterogeneous reaction system, for example, so the weightage of that part is only about 1 mark or 2 marks in GATE exam. Now it is not a time to learn that. Okay, if you can spare time, if you have done all other subjects properly, then you can go for the learning. But if you are starting from day one today, then don't go for that. Instead of heterogeneous part, leave it, or just see the important section there and go for the homogeneous reaction system, where you can get easily 8 to 9 marks. Okay, so focus on those things which will give you marks, not on those things which will satisfy your ego. Okay, because we are not here to for ego massage or ego satisfaction. We are here to clear the GATE exam with good rank. Okay, so just see, if you see CRE and PDC, only these two subjects will give you the 20 marks almost. Math and FT will give you approx 28 marks. Means in GATE exam we have total 12 subjects including FT, but these 4 subjects will only have the weightage of 48 marks. So you can understand what we should do, will be our first priority. Okay, so that's how see the weightage of subjects and then do your preparations. Okay, if you are starting from day one today. Okay, and the people who are already doing the preparations and all, so you already know that. The people who are from the GATE course, you already know what I am trying to say and how to do the things I have already told you. And the people who are outside the from outside the TGC, just be smart. If you have any doubt in your preparation, you can call on the office number. They will connect you with me. I will help you to do your preparation, to help you understand the basics and the technicalities which are required for doing the preparation in last 30 days, last 40 days, last 50 days. Okay, next time we will come with another video where we will discuss what things you have to keep in your mind while doing the revision, while doing the preparation in last 40 days. Okay, in last 1 month we will come with that video next time, where we will tell you how you can improve your revision strategy, your preparations, your marks in last 30 days. So be there with guys, and if you have any doubt or you us want a video on any particular topic, then just mention that in the comment box. We will love to help you. Okay, so again I'm repeating at last, before ending this video, focus and spend most of your time on the scoring subject, on the scoring topics if you are starting from today. Okay, but and even in your revision as well, if you are doing that from so long, still in your revision spend most of your time in the scoring subjects like these four subjects can have the combined weightage of 48 marks, almost 50. So here you can easily get 40-45 marks. And from the remaining 8 subjects, can't you get 30 marks even? So 45 plus 30 give you 75 marks. 75 marks means definitely top 50 rank. Definitely, guarantee. You just come to me, I will write that same thing on a stamp paper as well. Okay, that 75 marks means definitely top 50 rank in chemical engineering. Okay, it is not possible that you are getting 75 marks and your rank will be out of 100. No, 45 marks 4 subjects and remaining 8 subjects only 30, you will get 75. Simple, such a easy thing. It is very easy to get good rank in GATE exam in chemical engineering. but obviously not simple, because everyone can get it. That's why it is easy, but everyone will not get it. So that's why it is not simple. Okay. If you have understood this, wonderful, it will help you. If you haven't, then no problem. God bless you. Good luck. See you guys. Take care. Tada. Bye bye.